Hi folks, Mr. Ackerman here. This is part 2 of the video that talks about acceleration due to gravity and terminal speed. In part 1, we really only got into the grade 11 ideas of solving kinematic equations where an object is moving in what's called free fall, that is, accelerating due to gravity and there's no air resistance. And if you remember at the end of that video, I had to go teach a class, so I had to stop it there and break it into 2 parts. This is the second part where we deal with the grade 12 idea of drag forces and terminal speed. So maybe I'll just write in here part 2, the long-awaited sequel. Yeah, well, maybe not exactly long-awaited, but hey, maybe I'll never be Steven Spielberg. What can I do? I'm just a guy. Anyway, let's move on to the topic at hand. So we left off talking about what happens when an object is falling through the sky due to gravity. It's accelerating downward at 9.8. But now what we want to do is start adding in the effects of air resistance. So in all those questions where it says neglect air resistance in order to keep it grade 11 style, now we're going to get rid of that and we'll add it in. So what I'd like you to do is think of an example where you personally have experienced air resistance. And I think you all have had this experience before. Think of driving along in the summer, it's a beautiful day, you roll down the window and you stick your hand out the window. Maybe you're on a side street going 40 kilometers an hour, that's usually the posted speed limit. So let's write that in, 40 kilometers per hour. And you get a nice breeze on your hand and it feels good. And then you turn out onto a main street where the speed limit is 60 kilometers per hour. Going a little bit faster, it's still pretty pleasant. You go to the highway and now you're going 100 kilometers an hour, and now you're not so sure it's a great idea to hold your hand out the window because it's actually getting pushed back quite a bit. Well, what does this tell us? I think as you can see pretty clearly, as the speed increases, so does the amount of force that you feel on your hand due to the wind. Well, we have a name for that force. It's called the drag force. Sometimes it's given the symbol F. If you remember from grade 11, force is a vector, therefore it's got the vector hat, and a little subscript drag. So you might see it written this way. It's also known as air resistance. Okay. Now, that's one factor that we can clearly see, is that speed affects the amount of drag. What are some of the other factors that affect the force of drag? Well, another thing you can do while you are moving along with your hand out the window is you could try holding your hand so that your palm is sort of catching the wind. In other words, hold your hand out the window so that your hand is facing, the palm of your hand is facing forward. And so you're almost catching the air in your hand. As you go faster and faster, your hand gets blown back. But something interesting happens if you now turn your hand so that your palm is facing down toward the road. Now it's just your fingers or the side of your hand, maybe your thumb, that's sort of cutting through the air, almost like an airplane wing. And now all of a sudden, there's a lot less force that's pushing on your hand. Another place you see this is if you watch Olympic skiing, downhill skiing. What do you notice that the skiers do when they really want to go fast? They tuck their body in and they try to make their profile as small as possible. So what is this telling us? It's telling us that the shape of the object as it goes through the air affects the amount of air resistance, and also the what we call cross-sectional having trouble getting that in there. Cross-sectional surface area. What that means is the physical area, square centimeters or square meters, that are facing in the direction of movement. These two things affect the amount of air resistance. You see it all the time in terms of shape. If you look at cars, they're designed to cut through the air. Now, I'm not a great artist, but I'll do my best here. You don't see too many cars that are shaped very boxy and square. You tend to see cars that are shaped more pointed at the front. And this, of course, well, one of the reasons anyway, is that they want the car to be a little more aerodynamic. So as they're moving forward, this shape is helping them to cut through the air. And also, you probably get an idea of this if you know a little bit about airplanes. You know that around the 1940s, the mid to late 1940s, when jet engines were starting to be developed, they started changing the shape of the airplane from the more bulky, boxy type into the kind we know of today, more of those jet fighters that are really pointed in the front. Here's my best attempt at a fighter plane. Okay, not too bad, but I'm not quitting my day job as a teacher and going into art, that's for sure. Nice and pointy here. Why? Because we want to make the cross-sectional surface area minimal. Another example of this, if you watch the game of football, American football, I'm not talking about the football that most of the world plays, but this football, when you see the quarterback throw the ball, he always throws it in a spiral. You'll see the ball spinning, and it always keeps the pointy end here going forward. In other words, he doesn't throw it so it's tumbling end over end. That's like a bad throw, something I would throw. Instead, he throws it with a nice tight spiral, and it goes through the air, keeping the total surface area that's facing the air as small as possible, as opposed to when the football tumbles vertically like this, and you get a bad throw. And now the surface area is much larger as the ball moves through the air. One of them has more air resistance, one of them has less. I think you know that this one has less surface area. And so we see right away that the drag force, F drag, what do we know about it? It increases with the surface area, and it also increases with the speed. And therefore, if we want to have very little drag, we try to keep these as low as possible. Of course, sometimes you need to go fast, like with a jet airplane, therefore you keep the surface area small. Sometimes you can afford to go slow and keep your drag low. An example of this, if you go biking on an afternoon when it's really, really windy and the wind is blowing in your face and it's just making it a real annoyance to bike, because every time you start biking and pushing harder, you go faster and then you get more air resistance. This is an example where you might want to just, you know what, until the wind dies down, just going to pedal slower and so be it. I'm going to drive a little bit slower on my bike because I don't want to put up with all the wind resistance. Okay? So these are a couple things to think about as we move on to an actual analysis of how these ideas are going to affect us objects falling through the air. So let me close this off and go on to another page. I'd like you to imagine an object actually falling. And in class we're going to do a little lab demonstration or a mini lab, an investigation, where we're going to take flat-bottomed coffee filters. You know those coffee filters that have kind of this shape? We're going to take those and we're going to drop them through the air so they fall down. And these flat-bottomed coffee filters, if you actually held one up so you could see the bottom of it, it would be a circle. And so we say that this flat-bottomed coffee filter, which is round, has a cross-sectional surface area that is circular. And you could even imagine, here's the radius of the circle, and the cross-sectional surface area would of course be pi r squared. So keep that in mind. What we're going to do is we're going to drop these through the air. And I'd like you to imagine, before you actually get to class tomorrow and you see us do this lab, what do you think the velocity time graph might look like for this object? So over here we're going to make a little prediction of what the velocity versus time graph is going to look like. And we're going to do it with what's called a thought experiment. We're going to try to think our way through to knowledge about reality. That can be a dangerous undertaking at the best of times, but I think you're going to see it actually works out nicely here. So, first of all, what's the first thing that's going to happen? Well, at first, we're going to drop this coffee filter, and its V1 is going to be 0, of course. And so there is no movement. That means there's no air resistance, because as you remember from going through from putting your hand out the window as you're driving through the air on different roads, the slower you go, the less air resistance. Drag forces depend on speed. So with no speed, there cannot be any air resistance at all, which means that the only force acting will be gravity. So we have gravity only. And what do you know happens when you let go of something and only gravity is acting? You get 9.8 meter per second squared acceleration. And therefore, at the beginning of falling, when the speed is very low, when the drag force is very low, when I can safely assume that F drag is very nearly equal to 0, if not 0, I'm going to get a sloping up of my velocity time graph with a slope of 9.8. And why is the slope 9.8? Because you remember that slope on a velocity graph is acceleration. So we can sort of think our way through to a bit of knowledge here that what we're going to get is slope 9.8 in the beginning. Okay, now back to our thought experiment here. You begin falling a little bit more, and of course you pick up speed. So now the speed is not 0, the speed is greater, or the velocity, however you want to think of it, is greater than 0. Now you're picking up speed. Let's think about what happens. As you pick up speed, going back to our thoughts about drag, more speed, more drag, right? Therefore, all of a sudden, you're going to be dealing with a little bit of upward force to compete. Call that the upward drag force that is slowing us down. Remember, drag always acts opposite the direction of motion, like when you're biking and you feel the wind pushing against you. So what have we got here? We've got drag down, but we've got drag up, but we've got gravity down. Now, think back to grade 11 free body diagrams. If you've got an object like a coffee filter that's feeling drag up and gravity down, there's still a net force down perhaps, but it won't be as great as it was in the beginning when drag was nearly 0. So this part here, let me just get a color. This part here was early on. But this part here is later on, maybe in the middle of our falling. And so what's that going to do? It's going to mean I don't have acceleration like I had before. I got a little bit less acceleration. Maybe not 9.8 like I had here, something less than 9.8. I don't know the exact number, but I'm going to put acceleration is less than 9.8. And furthermore, that means that on my graph here, which we're starting to draw, I'm not going to have a slope of 9.8. I'm going to have a slope that's less than 9.8. I don't know, maybe something like that. Okay? And what I can do here, just to remind you, slope less than 9.8. Anyway, fast forward a little bit later on, and now what's going to happen? I'm going to be going even faster, because as you accelerate, you pick up speed. That's what this graph is showing. And so once again, thinking about drag, more speed, more drag. So we go back here, and we analyze that now, pretty soon, even though I'll be going faster still with more drag, I'm going to get to a point where the gravity force is, believe it or not, pretty close to the same value as the drag force. And think back to grade 11. What happens when two force vectors are opposing each other and they're the same magnitude? Well, if they're the same magnitude, then eventually that means the net force, remember that? Net force will equal 0, which means acceleration will be 0. Pretty soon there'll be so much drag that gravity won't be able to speed things up anymore. And then, circle this in yet another color to help you keep it straight. Sorry, it might be a little hard to see that. Switch it to green. This is later still. You will finally be at a case where the acceleration is 0. So what's that going to look like? Well, it's going to be a flat line on your VT graph. And I'll write it in for you to remember. Just like that. Now, this is a pretty kinky, sort of kinked graph, right? It's not like that in real life. In real life, the bending of the graph happens much more smoothly, and you're going to see that in tomorrow's lab. However, this is just a thought experiment in kind of 3 parts, 3 phases. So what you can expect tomorrow is VT graphs that curve and level off. And so what you're going to see in your textbook are some questions where they ask you to imagine that this is what's happening, and they ask you the kind of questions that we've already solved in part 1 of the video, but with different characteristics of a VT graph. So as an example, you might see something where they do this. They say, just for argument's sake, pretend that initially, due to wind resistance, the acceleration is, on average, less than 9.8. Maybe just as an average, pretend it's 8.5 meters per second squared on this VT graph. And then assume that that lasts for a certain amount of time until the drag force equals the gravity force. I don't know, suppose it happens for, however many seconds. I'll tell you a little bit more about this later. And assume that after a certain amount of time, drag force equals gravity force, and now there's no acceleration, so now the acceleration becomes 0. And then they're going to ask you questions about how far has an object fallen, how long might it take to hit the ground, etc. It'll be the same kind of kinematics that you've been dealing with before, only in 2 parts, because you have 2 different kinds of acceleration. They're going to mention a term to you which is extremely important, and it is the speed that you have to be going to make the drag so great that it's equal to gravity. We have a name for that. It's called terminal speed. And it is that maximum speed that an object can fall at, because at that speed, it's going so fast, remember this, that the drag force is so great that it exactly balances gravity, and you can't speed up anymore. You have 0 acceleration. It's called terminal speed. It's sometimes written v with the subscript TERM. And I'm going to leave you with an application of terminal speed, which I think you'll enjoy. So this is right out of the textbook. I forget exactly what page, but it's from Physics 12 by Nelson. It's talking about a volcanic eruption and the fact that volcanic eruptions release enormous amounts of dust up into the atmosphere. And dust particles, of course, are very, very light. In fact, they're so light that, going back to this analysis, they don't have much gravity force acting on them, which means they don't have to move very fast before the drag forces as they move through the atmosphere equal gravity. And this, believe it or not, prevents them from falling back down to the ground after they've been ejected from the volcano. So volcanic eruptions release a lot of dust, obviously, you can see in the picture, and they keep that dust in the atmosphere for a very long period of time. This article talks about how, or this caption rather, talks about how these particles can stay up in the air so long, and there can be so many of them, that they can actually reflect a substantial amount of sunlight back into space, thereby cooling the Earth, kind of like the reverse of global warming. This is not some sort of fantasy. This is an actually documented effect due to volcanic eruptions. In fact, some climate scientists have proposed, if global warming gets too far out of hand, maybe we should inject aerosols, fine particles, into the upper atmosphere in order to reflect back a certain amount of light and cool the planet. Sounds great, but how much would be a safe amount? What if we cooled the planet too much and that led to crop failures? Crops need sunlight and a certain minimum temperature to grow. What if it led to an accumulation of ice in the north, in the extreme north and south, and perhaps even an accidental ice age? This could be a disaster. So the climate is certainly something we don't understand too well. Should we be tampering with it? Who knows? But certainly something to take into account. All right, folks, so that's just an interesting example of terminal speed. One other one that I'll leave you with, which you can check out on your own, go back and look up this guy. Remember Felix Baumgartner, who jumped from 120,000 feet above the surface of Earth, well above the Earth's atmosphere. So he actually fell through, or fell toward Earth with no air resistance to slow him down, at least not until he re-entered the atmosphere and began to encounter drag. Watch it, see what speed he gets up to, and see what his terminal speed was. See if you can figure this out. As a challenge, what would his VT graph look like? This is a very interesting application we'll talk more about in class. And one last thing, I know you want to go, so do I. Here's the very last thing. A great video about the Apollo astronauts who went to the moon in the late 60s and early 70s. The moon, of course, has gravity. It just doesn't have air. So what did they do up there? They took a hammer, something heavy, and a feather, something light, and they dropped them from the same height. And I want you to watch what happens and see if you can figure out why that happened. And maybe also if you watch this video here about a feather and a ball bearing, again a light and a heavy object dropped in a vacuum chamber, you'll start to get a better idea of what is drag, what is air resistance, how do they relate to terminal speed, and how does that affect the rate of falling objects. All right, folks, thanks for watching, and I'll see you in class.